Now, once you have the ultraviolet finiteness, it doesn't mean that you have a satisfactory theory of quantum gravity, by no means. But it's certainly one of the key issues in understanding quantum gravity theories. What's their ultraviolet behavior? And the good thing is now people are again looking at these theories. Okay, so here's the summary. So the first thing is we reformulated perturbative quantum theory into a form, this on-shell formalism, that allows us to attack very difficult fundamental problems, either in phenomenology or some questions in quantum field theory, in quantum gravity specifically. So there's the LHC computations. And then I showed you this remarkable harmony. Just two examples. There's an enormous number of examples you could take of remarkable harmony, relations that you find in scattering amplitudes. But the ones I showed you was this duality between the color and kinematics, and related to that is this relationship between gravity theories and gauge theories. So this would be gravity and strong interactions. And at the end, to us, it doesn't look like perturbative gravity and gauge theories are very different. And most certainly, they're surprisingly tame in the ultraviolet. And we covered this phenomenon of enhanced cancellation. So there's definitely something going on which does not happen in gauge theories. And that makes the ultraviolet a lot tamer than you would have expected. So the final summary is with these new on-shelf theoretical tools, I think we can expect many more exciting developments in the coming years in both phenomenology and in more formal areas. And if you want to read more about this in non-technical, there's this on the gravity that Herman Nicolai wrote a PRL physics viewpoint. So it's a something non-technical. We have a Scientific American article. It's actually extremely well written. Let's just say the editors are quite good, so they know how to write. And then there's Tony Z's book, Quantum Field Theory in a Nutshell. So if you have the first edition, I have bad news for you. You have to throw it away. Get the second edition. There's 4 new chapters in there that tell you about the scattering amplitudes. Okay, and if you want to be amused, try Googling that and go 20 seconds into the video. Okay, thank you.
About this enhanced cancellation, can you trace to some symmetry properties of the angular A supergravity, like
no,
duality?
Actually, yeah. Well, not to n equals 8 supergravity, but it's a general property of gravity. And in fact, we have traced very carefully. Yeah. You can hear me, right? Oh, great. So we've traced it to the duality between color and kinematics in a case of D equals 5 half maximal supergravity. We can find exactly what the origin of the cancellation is. And the origin in that case is that in Yang-Mills theories, there's constraints on the types of counterterms you can have. So the Yang-Mills theories, the gauge theories, they're renormalizable. So that prevents certain types of color factors from appearing. And when you constrain those color factors to not be divergent, it's exactly that constraint that makes this corresponding supergravity finite. So I believe that it's the duality between color and kinematics that'll provide the general explanation. The unfortunate thing is, as you go to higher loops, it gets a lot more complicated. The 2 loops had a special property that made it very simple to analyze. I think we do that together. Yeah, with Utin. Actually, I should. Oh, that was really dumb of me. So the 3, forgot to say, the 3 loop work on n equals 4 supergravity, Utin. So we did it when he was at UCLA. So Yuten and two of the students.
Does the enhanced cancellations of through gravity hint at hidden symmetries of the theory?
Sorry. Well, I think I heard the question. So it's not a standard. It's not a standard. It's not due to a standard symmetry. That I'm quite confident of. Over the years, we've gained quite a lot of experience in knowing what the symmetries are doing. There's actually a very nice paper from Michael Green and Bjornson on where they analyze this question. You can actually find the paper very easily. It's the only paper, I'm sure, that has 24/5, the number 24/5, written in the title. And in that paper, they explain that the symmetry, the standard symmetries will only give you a certain amount of cancellation. Anything beyond that is what we would call enhanced. So in a sense, we could say anything Bjornson and Green didn't find, that's an enhanced cancellation.
Somewhat different point of view, and I'm not sure that I'm quite correct, but Yang-Mills theory has a good high-energy scattering behavior, and Yang-Mills theory is of course proven to be normal, whereas relativity theory has a bad high-energy behavior.
Mm-hmm.
And that bad high-energy behavior may be related to the non-unitary behavior of the relativity theory.
Well, these theories are all unitary. I guess what you're referring to is it's just because it's dimensionful coupling constant. Then, as you increase the energy, in fact, what happens is each order of perturbation theory grows, and that's all true. So the statement that you're making is that the perturbation theory of gravity is really bad, right? The lack of convergence. But I'm not scared of that. That, I think, is just a technical problem. Even Yang-Mills theory, it's true that gauge theory is, it's true gravity theory is much worse behaved, but as you very well know, perturbation theory does not converge either in gauge theory. So I think that we just need to wait. If the theory is ultraviolet finite, that's a big deal. It means there's something deep going on in those theories. Then you say one of the issues you'd have to worry about is how you're supposed to define this theory beyond perturbation theory, because of this problem that the perturbation theory is so poor as you go to high energies. And that, one thing at a time. I think that I would not touch that question until I would understand the symmetries that are causing exactly these cancellations. Let's assume it's finite. Clearly, that whatever is causing it to be finite needs to be accounted for in anything you discuss about high energy behavior. So I think that just needs to wait until we get there. Yeah, something wrong with it.
So for the Hello. So for the experimental part, has the unsureness method implemented in other multicolor generators?
Yes, there's a lot of them. So it's even been implemented in part-time showering programs. So this would be next to leading order based part-time showering. But anyway, there's quite a lot of. Sorry, it's just a little slow here. I need a new laptop. No. We don't do computations on this thing. Almost. Anyway, there's a long list of programs, and there's new ones I'm sure that I don't have on the list. Sorry. Okay. Anyway, maybe I'll show you afterwards. There's quite a long list of programs that use these ideas. It's really the way things are done now. Almost everybody. There's various other ideas that people apply, but by far this is now the dominant one that people use.
Any other questions?
Do you expect some theoretic explanation for the color kinematics duality?
Yes, but it's not going to be anything standard. So there's been already some work, quite a bit of work, and in one case, which is self-dual field theory, it's very well understood. So there's a paper from O'Connell and Montero that explains this in terms of an underlying diffeomorphism invariance that's hidden in the Yang-Mills theory. To go beyond that, there's been some work, but it's more complicated. The explanation you're not going to find in a Lagrangian. That I'm quite certain of. At least I'd be really shocked if that was true.
Any other questions?
I don't know whether this question will be up to Mark, but still following this analogy between, say, why the IR behavior is so different between Yang-Mills and gravity?
There's been, well, actually the IR behavior is not quite as different as you think. The IR behavior has to do with the behavior of soft gravitons or collinear gravitons inside loops. But the basic behavior, if you study it, it turns out to be very similar. There are some differences. In fact, the key difference. Are you talking about confinement? Maybe.
Yeah.
Oh well. I see. Okay. Correct answer for the wrong question. Okay. So the confinement is controlled by what the theory does after you integrate it. For example, the beta function, you actually have to do an integral. Now, just because there's this relationship at the integrand level, so there's a very simple relation that we use that allows us to map one theory into the other. After you do the integrals, it doesn't mean that the physics comes out the same, because when you square the numerators, so you get more powers of loop momentum, you get a different set of integrals. So just the dynamics, what you get out after you carry out the integration when you study the physics, can be quite different. So it's a relationship at the integrand level.